Insider attacks on computer systems are really not only about intellectual property or data leaking from organizations. They can indeed harm people. And today I don't want to speculate about the recent stories on hardware implants on server mainboards. But we've all seen in public reports, I think we're all aware that the lines between our digital lives and personal safety are actually becoming increasingly blurry. Based on the public reports on the Twitter insider data leaks that we've seen, we may actually never know what the direct impact on some individuals' lives was. But what we know is that some journalists, security researchers, and so on were actually notified that their personal accounts were directly impacted and that there was some at least alleged connection to state-sponsored actors. So when talking about insiders and what insider attacks can do, what do I mean with insiders? Within the scope of this talk, I mean any person who has privileged access to potentially relevant informational resources. That can even include external parties. External parties potentially acting through remote control malware with privileges of those insider users. So this definition is actually intentionally broad. And look around you. Pretty much most people inside this room are insiders in one way or the other. Hardware protocol designers, software developers, but also logistics or retail shop personnel. Now, while the examples that I'm going to use in my talk will be based on Android and this particular ecosystem, I believe that my conclusions will apply a lot more broadly to other areas as well. If we look at mobile phones, what we have in our pockets today, then I think it's undoubtedly true that we currently have to implicitly trust a hugely long and complex chain of people and organizations to keep our phones secure and to keep the data that is stored on these phones actually private. Now, insiders in that chain may be individuals or maybe even colluding among multiple organizations. That picture, I have to admit, is a little bit simplified with hardware at the top, software at the bottom. Unfortunately, the real supply chain is a tiny bit more complex. So let's zoom into a still simplified point of view. Let's start here at the top left corner with chipset designers. That is actually making designs here in this space for CPUs, main memories, sensors, GPUs, or low power, always on DSPs for voice assistance or activity recognition. Those chipset designs are shipped to fabs that make the actual chips. Then we have a party that's called the ODM, the so-called original device manufacturer, which combines these multiple chips into a coherent hardware system design, which then gets shipped off to an OEM, or original equipment manufacturer, which then finally boxes and labels that product. That is actually the first company name that most users will be familiar with, because that's what's written on the outside of the box. Now, on the software side, it's at least as complex. The OS vendor writes probably the majority of code, but this integrates chip drivers and low-level hardware initialization code from the chipset designers. This is then bundled up by the ODM and OEM with third-party services and sometimes also own APKs, own apps that are put onto this device. Then the complete ensemble of hardware and software is finally shipped to end users, typically through multiple hops to an online or retail store, at which point shop personnel may take the phone out of the box, help with inserting the SIM card, help with walking through the first use wizard, even set up some dummy accounts. That is perceived as a value-added service. Of course, any party within this long chain could potentially add malicious code to the device, either in a broad sweep for all users of that particular product, or even more dangerously, targeted to only select individual users. It seems daunting, even impossible, to try to get any degree of reassurance or guarantee that the device is actually working as expected. But let's not give up. I'm proposing let's break the problem apart here. The first principle that I suggest is to reduce this complexity by decomposition. every component in such a complex system should be trusted only as far as strictly necessary. The component should be as simple as possible in itself, and we should only have as few of those trusted components as we can get away with. Now, this makes it easier to detect both genuine mistakes and malicious insider attacks. One example is the use of so-called secure elements. Secure elements are crypto coprocessors that can store and use cryptographic keys, and therefore not have to use those keys on the significantly more complex main CPU. Both in the server space and on mobile phones, these are typically used, and given Spectre, Meltdown, Rowhammer, Foreshadow, and all the other hardware-level attacks that we've seen and that we're probably about to see, this seems like an important first step. Another example from Android is Project Treble, which recently created so-called hardware abstraction layer components, or HALs, that mediate access between core OS services and drivers running in the kernel space. By decomposing those interfaces, every single one of those HALs can be made simpler and can be sandboxed, in our case, with SE/Linux rules. But let's talk about the different layers in which we have such hardware or software components. The lowest layer, hardware itself, is still hard. So for details on that, I happily refer to yesterday morning's excellent talks by Cynthia and Ryan on hardware vulnerabilities in general and hardware security modules in particular. Within the scope of this talk, I would rather focus on the software side. The lowest layer of the software stack is what we typically call firmware. Firmware is what runs on all the auxiliary processors, from radios down to those secure elements. Even if we assume that trusted hardware to be simple, and that assumption might be warranted, simple enough to be actually correct, then the firmware running on these auxiliary processors can still make the whole system insecure. And this is true for all such systems where the firmware can be upgraded. Insiders with full access to their respective signing keys could create firmware that still leaks those user secret keys and therefore makes them available for further escalating attacks. Now, since that is true for all the systems where firmware can be updated, from rack mount hardware security modules used in the server space to enclaves on more complex CPUs or systems on chips, down to smart card level chips, we need to fix that problem. And as Ryan mentioned yesterday, the fact that most such HSMs are black boxes is a huge potential risk for such insider attacks. Now, there is one hope, because there is at least some primitive low-level loader code that in itself is typically not modifiable. And this is where you can start to protect insider attacks. So in the following, I would like to pick 3 specific examples of recent changes that were made to the Android platform to mitigate better against insiders. Android Pie is the first release that introduced the definition of Strongbox, which is an API to exactly do that, to store and process cryptographic keys on dedicated secure hardware. And it is strongly recommended for that to be implemented in a way that whenever the firmware on such a secure hardware is updated, users' secret keys are either wiped or otherwise made inaccessible. Unless the user's knowledge factor, and by knowledge factor I mean PIN code, password, or pattern, is known at that time. It can be implemented in different ways. The Google Pixel 2 and Pixel 3 implement these differently. In Pixel 2, in the former case, we use a secure element available by NXP, and this was modified with 2 key points. The first key point being the Java card applet that actually stores these cryptographic keys, that stores the user secrets, does intentionally not implement any backup code. The second key change is that the OS loader of that NXP secure element OS itself has been modified to only allow an update of the OS itself when that particular Java card applet has previously been uninstalled. On Pixel 3, it's different because there's just 2 firmware slots. They're just updated atomically. And whenever a new firmware is installed, it's put into a hold state. And to transition to that active state, first, the user knowledge factor has to be modified, which again is ensured by the low-level firmware. In both cases, the effect is the same, that whenever firmware is upgraded without knowing the user's knowledge factor at that time, the user's secrets are wiped or made inaccessible. Now, there is still that other case that if you have physical control over the device and you don't have the user knowledge factor, you can still reset and update the hardware and the firmware running on that hardware, which is important for cases like repairs, RMA repairs, and so on. But in that case, when updates are forcibly installed, this behavior ensures that user secrets cannot leak from the device. Now, one layer up, the system software, or that we typically call the OS running on a main CPU, the trade-off has to be a little bit different because this layer should be updated much more frequently. And because of the frequency of those updates, that should happen in the background so as not to bother users. So we need a different approach than wiping and re-importing the data every time such an update happens. I propose that for this layer, transparency is key. With open source operating systems, those images released and signed by a manufacturer could be verified by third parties, taking the source code, analyzing the source code, rebuilding it in a reproducible way, and verifying that those hashes actually match what has been published. Now, if we add those hashes to a public timestamped append-only log, it makes it verifiable. And much like certificate transparency, so yes, I'm intentionally not saying blockchain here. There are other ways of having an append-only log. Much like certificate transparency for TLS certificates, thank you. There are simpler ways. Much like that, that only leaves an adversary two possible ways. Either a tampered with, a potentially malicious firmware is put into that log, at which point maybe the firmware itself is only targeted to a few devices. Maybe the firmware itself is not public, but the existence of such a firmware is being made public by putting it into the log. And the existence of that firmware being public is in itself a very strong deterrence against such targeted attacks. Option B, not put the hash into the log, not put the firmware, the existence of the firmware into the log, in which case OS uploader code can start to refuse applying that update when there is no proof of inclusion in any of those logs. While this does not automatically make the firmware running on a device secure, it makes updates transparent and creates a chain of auditability. And again, Android Pie enables a first step towards such a log. The so-called VB meta structure, which is basically a hash over all the read-only partitions that make up the basic OS firmware, is passed on from the low-level bootloader that actually verifies that during boot up to the so-called keymaster component. Keymaster is one implementation, software implementation running ATE, and the other component would be Strongbox. So this hash is passed to both implementations and can then be included in what we call the key attestation certificates. Now, how can we use that? If any third party can now download images for, let's say, a Pixel 3 device, use the recently updated AVB tool binary to independently create that digest, the VB meta digest, and ask the running system for a new key attestation certificate for a newly created key that is stored in the secure hardware. That key attestation certificate will include that VB meta hash of the running system in the certificate, and it can be independently verified of what is actually running on a device. In the appendix of my slides, which will be online after the talk, I have more technical detail on how that actually works and how everybody can reproduce that. Now, the next logical step would be to establish a public log of all such released system images. And we are currently evaluating various options to do so. If anybody wants to cooperate on such efforts, please reach out to me. We're very open to collaboration here to make this a global log. The last part I want to give a specific example on is backups, which are at the intersection between the system OS layer and apps. Android Pie, again, introduced client-side encrypted backups, which we could also call end-to-end encrypted from the point of view of Google Drive being the actual store for the backups themselves. And I'd like to run through the core parts of that protocol right now, because after all, this is Enigma, so I wanted to have some crypto on the slides. Crypto as in cryptography, not cryptocurrency. Thank you so much. And therefore, let's take here two phones. On the left side, we have a phone that creates a backup, client-side encrypted. On the right side, we have a phone that wants to restore that backup. And in the middle, we have the Google Cloud infrastructure that facilitates that. As part of that Google Cloud infrastructure, there is what we call the Google Cloud Key Vault service, which uses what we call trusted hardware modules, which effectively are just Titan chips that are on the server side instead of the phone. But pretty much the same guarantees for insider attack resistance on updating firmware on those Titan chips that act as the trusted hardware modules are in place there. So this, what I said before, holds here as well. First step, the device wanting to create a backup fetches a public key of a cohort of those trusted hardware modules from the cloud and asks the user for the local knowledge factor, for example, the PIN code, pattern, or password. Now, a new key, the backup key, local client-side backup encryption key is created, and that is wrapped twice in 2 layers of encryption. First layer, the inner layer, is with a key derived directly from the user knowledge factor on the device. And the second layer is just public key encryption with the public key of that trusted hardware module. This doubly encrypted backup encryption key is shipped to the infrastructure and stored for later use. Then, when the second device, not connected to the first one, wants to restore from this backup set, a new key, the key dash here, the so-called claimant key, is randomly created, and the device also fetches the public key for this cohort of trusted hardware modules. Now, asking the user for the knowledge factor of the previous device where the backup was created, the key derived from this PIN code, password or pattern, together with the claimant key is encrypted with the same public key and shipped to the cloud. Now within one of those trusted hardware modules belonging to the same cohort, a new instance is spun up, and everything inside the green box stays within the trusted hardware module, and the intermediate results never leave that module. So first, we remove the outer layer, decrypt with the private key that's only kept in there, and try to use the key that comes from the new restore device. Try to use that key on the inner layer of encryption. If that works, if that can actually be decrypted, and we know that the PIN matches with some failure counters and so on, and upon successful decryption can actually re-encrypt, rewrap that backup encryption key with the claimant key, ship it to the restore device, and the restore device can actually then decrypt the whole backup. That is strictly stronger than just having a very often low entropy PIN or password that's used as the user local knowledge factor, because this computation is done within the trusted hardware model. But even if that went wrong, even if this didn't work, the cloud side didn't work as expected, it would still be protected by the local cloud, by the local knowledge factor. So a strong password together with this doesn't make it any weaker. It just makes it stronger. With insider attack resistance implemented in the trusted hardware module server side, even admins with full Google Cloud access cannot brute force users' knowledge factors at this point. So again, this is the third and last specific example I wanted to give for what we did on Android, specifically in the last release towards insider attack resistance. Now, moving to the top layer, apps, and what apps typically do, what we call dynamic code loading or DCL, is both easier and harder from an insider point of view. It's easier because what apps can do on the phone is limited by their permissions. It's not perfect, and thanks, Serge, for your talk pointing out that, yes, the app ecosystem does have issues that need to be solved, and this is a very hot topic that many people are working on. But on the other side, if an app is removed from the device, all the side effects vanish. So because of the sandbox, an app can only use anything within its own permissions within the sandbox. On the other side, it's also a much harder problem than the system OS layer simply because of the sheer scale. There's millions of app developers. It seems pretty unrealistic that all of them would switch to open source and would be independently verified of what's going on in there. So auditability will get us some step, but it's not the full picture. And we are still trying to find a good balance together with the dynamic code loading that's going on, where the most obvious example is web browsers, web apps that just download JavaScript and execute that within the app's process, to find a good balance that will allow legitimate applications at this scale and diversity that we see, but prevent or at least mitigate against insider attacks at the app developer's organization, or libraries, SDKs, included by those developers. And that is a very active problem that is still a hot field for research and development. And we are actively looking for collaboration. So if you are interested in working on this problem, please talk to us. We are happy to collaborate here to work together. Coming to the end of my talk, my call for action here is that everybody who is building trusted systems should think hard about insider attacks. If you are part of the Android ecosystem, for example, at an OEM or developing apps, then I ask you both to support consolidated efforts to deal with this problem and to look into your own organization on how to deprivilege insiders. And auditability is a key defense against insider attacks. If you can, make it technically impossible for insiders to perform an action against users. Make every single component simple and enforce code transparency. If that's not possible for various reasons, then make it evident that an action happened. Open source can help, as can logs and notifications. But these measures don't make insider attacks impossible. However, they can act as very strong deterrents against such attacks. I would like to close the loop and bring the discussion back to Android. When talking about security and privacy in the Android platform in my role, I would really personally like to be able to say, don't take my word for it. I can't abuse user trust because we made it technically impossible for me to do so. We're aware that we're not quite there yet, but we're getting closer step by step. So let's work together on this one. Let's take ourselves out of the trust equation and make it impossible for all of us insiders here to actually become attackers. Thank you.